Hello, my name is Leonard Bach, and on behalf of our team from the Institute for Marine and Antarctic Studies at the University of Tasmania, I'm providing a short introduction on our fieldwork studying what is known as Ocean Alkalinity Enhancement. The research has started in late 2024, and the first phase will likely finish in the first quarter of 2025. I'm going to start with explaining what motivates this study. Then I'm going to talk about what ocean alkalinity enhancement actually is. We're going to talk about the study design and then finally the goals of the study. So this field experiment is motivated by climate change. And as most people are aware of, the Earth is currently warming at a rapid pace, mostly due to fossil fuel emissions. In the scientific community, it's generally accepted that warming should be kept below 2 degrees Celsius to maintain the Holocene mode of operation of the Earth system. So what this means is that if human activity drives warming beyond 2 degrees Celsius, there's an increasing chance that the Earth climate transitions into some prehistoric state that occurred long before humans existed. And yeah, this would likely be a very hostile climate for humankind. So policy has been made aware of this problem a long time ago, but only responded relatively recently in a coordinated manner by agreeing upon the Paris Agreement. And the Paris Agreement basically says that humankind aims to keep global warming well below 2 degrees Celsius, ideally limited to only 1.5 degrees Celsius. Arguably, the Paris Agreement was the easy step because politicians would only have to come together and make an agreement. Hard enough, but what I will show you now is showing how much harder it is to achieve this goal. So here this plot shows on the x-axis time from 1980 to the year 2100, and on the y-axis it shows CO2 emissions in gigatons CO2 per year. 1 gigaton is 1 billion tons of CO2. And it shows the historical emissions above the gray area. So this is just how emissions evolved over time, over the last decades. And then the brown area shows how CO2 emissions would have to decline in order to achieve the goals set in Paris. And well, as we can see here, the reduction in emissions would have to be absolutely more or less instantaneous. So over 10 years, we would have to stop emitting any CO2 really. And many people, many scientists, many politicians assume this to be not realistic, that we're not achieving this goal. So the alternative or the add-on to that is, in order to slow down the rate of decarbonization, we would have to take out CO2 from the atmosphere, so CO2 that is already emitted to the atmosphere. We'd have to take that out to some sort of CO2 removal method, and the numbers that would be necessary are absolutely astronomical. So in case we were able to phase out fossil fuel emissions until roughly 2050, in that case we would still need 500 billion tons of CO2 removal until 2100. Which is a very, very significant number. And the problem is no one knows how this could be achieved. So the one thing that comes immediately into everyone's mind when you ask them how to get rid of CO2 in the atmosphere, most people would suggest forests and soils. And obviously these ecosystems do that. The problem is those ecosystems or those carbon reservoirs store carbon for very short time scales. So the carbon that is sequestered also goes out of the system and back into the atmosphere fairly quickly. So what we need in order to remove fossil fuel emissions, which come from a reservoir where carbon was stored for millions of years, is also a carbon reservoir or carbon sink where the carbon will be stored for certainly more than thousands of years into the future. And one of the ideas how to achieve this, so how to achieve durable CO2 removal, is ocean alkalinity enhancement. What is ocean alkalinity enhancement? So ocean alkalinity enhancement aims to increase chemical storage capacity of seawater for CO2. Now, I apologize, I can't do this without a chemical equation. So what you see here, the equation in the middle, is the marine, or the marine carbonate chemistry equilibrium. So when CO2 goes into the ocean, because it comes from the atmosphere, it's getting dissolved in the ocean, it reacts with water to form carbonic acid. This is the same reaction that happens when we create soda water for drinking, right? If we get the bubbly water, the same thing happens there. So CO2 reacts with water, and so part of this carbonic acid that is then formed dissociates into bicarbonate ion, which is this, and carbonate ion, which is this. And of course is acidity, protons, H+. So the influx of CO2 creates acidity. That is why we know this problem as ocean acidification. Now, what we can do in order to store more CO2 in seawater without increasing the acidity of the seawater is we somehow try to catch the protons. And if we do that, if we achieve catching the protons, then more CO2 is converted into bicarbonate and carbonate and allows atmospheric CO2 to come into the ocean. Now, how can we catch protons? And that can be achieved through weathering reactions, which I'll talk about in the next slide. The nice thing about this whole process is that it obviously counteracts global warming because it enhances the absorption of atmospheric CO2 in seawater, and it to some extent also counteracts ocean acidification. Ocean alkalinity enhancement is inspired by the natural process of chemical weathering. So if we just ask ourselves what will happen with the amount of CO2 that we currently put into the atmosphere over geological timescales, so over the next 100,000 years or so. So what will happen is that, of course, the atmospheric CO2 concentration will increase. So this data that I'm showing here is from a modeling study. So atmospheric CO2 will increase, and then atmospheric CO2 concentration will decrease again. And first, much of this decrease is just simply due to CO2 going back or going into the ocean, being absorbed by the ocean. So the ocean helps us to mop up the pollution in the atmosphere. And then over even longer time scales, so over 10,000 years or so, seafloor sediments start to dissolve and start catching the protons, the process that I showed on the previous slide. And even longer time scales, so 50,000, 100,000 years into the future, there will also be continental weathering processes. So protons will be caught, protons of CO2 from carbonic acid in rainwater, for example. And then the CO2 that was previously in the atmosphere will be washed via rivers into the ocean as bicarbonate. The thing is, of course, the problem here is that this process is extremely slow. So our anthropogenic CO2 that we emit now will be gone, but it will take 10 to 100,000 years into the future. Obviously, these processes therefore don't help us to mitigate climate change, which is essentially happening right now. So the question that ocean alkalinity enhancement aims to address is, how could this natural process be accelerated? Yeah, so one answer to this question is, so how can we accelerate, is relatively straightforward. We could start extracting minerals that enable the weathering reaction. We could extract those minerals, grind them to powder so that their surface area gets bigger. And then we transport them and distribute them all over the place. And the extraction, grinding, transport, and distribution will increase the exposure of these naturally CO2 absorbing minerals over the Earth's surface, and therefore speed up the process. Another potential idea to do ocean alkalinity enhancement is via electrochemistry. And here, seawater would be pumped into a facility, and renewable energy would be used to remove acid from seawater electrochemically. The acid would have to be removed, and this is a big environmental problem, but the acid-depleted water would be discharged back into the ocean and absorb atmospheric CO2. This will likely be less of an environmental problem. The issue with that approach is, besides producing large amounts of acidity that has to be dealt with, it requires quite a lot of renewable energy. So it has been estimated roughly 11.3 gigajoules per ton CO2. And for perspective, this like a large wind turbine, a very large one, an offshore one, would have to spin under solid wind for around an hour to sequester 1 ton of CO2. The big question, of course, is whether ocean alkalinity enhancement has any chance to work. And there have been quite a lot of mathematical simulations. And yes, it would most likely work, but in an idealized mathematical model it would. The open questions are, there's large uncertainty how ocean alkalinity enhancement, so here I abbreviated OAE, influences element cycling in the ocean, so how the biogeochemistry of the oceans would be affected by it. And then, of course, also if and how OAE, ocean alkalinity enhancement, would influence marine life. So these exact questions motivate the field study that we're currently planning and executing in Tasmania in late 2024. The study's design is as follows. So we go out into the field, into some shallower water, and there we designate a couple of plots of around 1 square meter. And some of these plots will be enriched with mineral powder considered for ocean alkalinity enhancement. So this little video shows how this would roughly look. We tested a couple of things over the last days, and here we test how minerals can be added to the seafloor, which is actually a surprisingly challenging task because the particles are relatively small and drift a little bit away through ocean currents. The goals of the study are twofold. So first of all, we want to understand, could ocean alkalinity enhancement lead to CO2 removal under real-world conditions, so outside of a mathematical model? And secondly, what are the implications of ocean alkalinity enhancement for marine life in sediments? If you're interested how the research evolves, then please follow our blog shown on this web address. And I also put the same link into the video description. With that, I'd like to thank you, and I hope that video answered some questions around this field study. Thank you.